Previously, we created a single crank, a connecting rod in two components, and a piston with a pin to hold the connecting rod small end. So the big end of the connecting rod will go inside the crank, while the small end will go inside the piston. So that is how we designed and created each of these components. Today, we are going to bring all these things together and make a single engine. In order to do that, we are going to be using the word joint over and over. And joint may mean something to you already. So it is important for us to define what we mean when we use joint in this class. It may not be exactly what you have been used to calling a joint. You know, you can have a joint to go and drink your gogoro or some other things you want to do. But the joint we are talking about here, you may have joints on your body, your limbs, your ankle. The joint we are talking about here is a little bit more abstract than that. So it is important to first understand the kinematic constraints in order to understand what a joint is. We must understand what are kinematic constraints that can take place between components. When two components are assembled, one of the constraints is that you know that in real world, you cannot pass a physical body through another physical body. But when you are drawing, the drawing doesn't know that, so it can pass them through. So the first thing is you want to constrain bodies so that they do not pass through each other. More than that, there might be some kinematic relationship between two bodies. That is, one may rotate on the other one may slide, they may have sliding motions, and they may have other kinds of motions that are allowed in reality. And they may have limits as to how far something may be oscillating around a point, but it may not go in a full circle. It may just go through only 30 degrees from a particular angle to another angle. All those kinds of relationships are called kinematical constraints. Now, so a joint defines these kinematical relationships, specifying what movements are allowed or not allowed. In a situation where no movement is allowed between two components, that circumstance is still represented as a joint. It is called a rigid joint. So when there is even no motion, you still call that relationship a joint. The motion allowed in a rigid joint is no motion. So when you say it's a rigid joint, that means that between the two components involved, there will be no motion. You know, I've been talking about components. I've not been talking about bodies. There's a reason. It's not an accident. You will see the reason for that shortly. The purpose of today's lecture is to use the joint abstraction to assemble matching parts, defining pairwise relative motion, and show implication of such relative motions on an assembly. For instance, if I have 5 things and I've defined and I take them pairwise and I define the relationships 2 by 2. By the time I look at if those relationships are enforced, when I now look at the relationships on the whole, you'll be surprised as to the implications of the relationship, because all that Fusion 360 is doing is just keeping true to the promise of the relationships, but that now has implication on the body, on the assembly as a whole. And there is no better way to look at that than in a motor car engine. A motor car engine contains all the mechanical parts that really demonstrate this thing. That's why we are using it as an example. We can use other examples, but that is an example that I found very convenient. We'll bring these moving parts together into a single assembly. As a specific example, we shall create the kinematic relationships to get the animated engine moving like a real engine. There will be logical attachments, and we shall distinguish those from physical attachments. So I want you to take note of the difference between an attachment that is logical as distinct from an attachment that is physical. Whether the attachments are physical or not, all that Fusion 360 will impose are logical attachments. So even when there is no physical attachment involved, I will explain to you some examples as we move on. You will see that it is now your duty to put the physical attachments there. We will also create stationary parts, because up till now, we have been creating only the moving parts. We have been creating the a crankshaft, the top end of the connecting rod, the body of the connecting rod, and then the piston and the piston rings. All these things are things that move. But the cylinder itself will not move. The engine block itself will not move. So we are going to create representatives of the cylinder and the engine block in this assembly procedure. So we could have created them separately, but they are so easy to do. So that's why we are just going to combine their creation with the assembly, as we are going to do shortly. Now, assemblies, components, and bodies. So far, we have been creating bodies from two-dimensional sketches. Bodies can also be created directly from 3D primitives, such as cylinders, boxes, and several other things that are already in three-dimensional. They can also be created from combinations or deletions from other bodies. So you can create a body by combining previously created bodies. You can also create a body by cutting portions of existing bodies to get a new body. So bodies can be created from combinations or deletions from existing bodies. Irrespective of the creation method, a body is a three-dimensional shape that can be used to add or subtract geometrical objects or simply geometry. If you watch Fusion 360 Autodesk videos a lot, when they say you want to add or remove geometry, what they mean really is that you are adding or removing geometrical objects from your design. But they will not go to those details. They just say you are adding geometry to your design, or you are removing geometry from your design. That's what they mean. This is pursuant of the final shape required in the design. In your design, either in your head or in something you have seen, you know what physical bodies should constitute the design. So you are going to be using bodies to make up the totality of the things that are going to exist in that design. Now, sources of bodies. Bodies, as we have noted, can come from two-dimensional sketches or three-dimensional primitives into solids. So a solid is a type of body. Most of the bodies we have created so far have been solids. Please note that there are other body types that are not based on solids. So solids are not the only way to bring in bodies into your design. The other types are surfaces. You can bring in bodies through surfaces. In a surface, all you are going to see is the exterior shape of the body. You are not going to see the internals. So it's just the skin of the body you are going to see, nothing else. So when you have that, you call that a surface. A surface has zero thickness. There is also 3D splines. 3D splines are for people who want to use Fusion 360 for graphics, for graphic arts. An artist can use it to do any artistic design that they want. Some engineers can also use T-splines, but we would bring in T-splines sparingly in this course because we are, not because it's not useful, but because we don't have time to go too much into the details of that. There are also meshes. Meshes are when the bodies come from other sources. For instance, you can bring them from SolidWorks, from Autodesk Inventor, the engineer. Oh, there are so many other Solid Edge, SolidWorks, Solid Edge, and so many other graphics software. When they come from other sources, they are usually coming in meshes. So you can have bodies, surfaces, T-splines, or meshes. Those are the different body creation objects you may have. The surface is a very simple one. So a surface is a tool that creates geometry of an outer surface of the desired body. It has zero thickness. Here, we decided to create a surface here. And to create the surface, all I just did is to take a simple geometry like an ellipse, and then just do an extrusion of that ellipse with zero thickness. You know, before we would make sure that there is a profile that's a close profile before we begin extrusion. But you can extrude straight from the line, and that will be okay. So that is it here. You create a 2D sketch. We start with an ellipse, use a surface creation object, say the extrusion, to extrude the sketch profile. either from its profile plane or from an offset plane through a distance, you end up with a surface with zero thickness. I'm so tempted to just go to my Fusion 360 and just do a demonstration of this straight away so that you can see how it works. So let me launch my Fusion 360 here. And let me just open a page of that. Say new, create new design. Okay, no, just open a new page. And if I create a sketch, on this surface here, and in that sketch, I can create an ellipse. Since I used an ellipse before, let me just create a polygon, a circumscribed polygon. This polygon has 6 sides, and then if I say finish sketch, so I can now go to the surface, part, and I can take the surface. I can say create extrude, and then I'm taking a surface here. You can see this is just a surface, and let's say okay there, and then we can take a look at it. Let us do an orbit. Let's do an orbit of this. Let me see an orbit of this. If I do an orbit here, free orbit, let's make it full. Okay, full. So I can pan it. This something is disturbing me. Okay, let me pan it down. So I can now make it orbit. So you can see this is just a surface. So you can have surfaces of all sorts this way. So that's how I created the ellipse I showed in the slides. So let us go on and continue our. So you can see, you can easily create the skin of the object. That is another way that we have not been doing. And you will see later on that we will use this to advantage. There are situations where this is a better way to bring geometrical objects into our design. But you end up here initially with a surface with zero thickness. You can later actually add thickness to it. That is the beauty of it. If you add thickness to it, it now has finite thickness, and that may be what you want rather than creating a solid at the beginning. So let's go back and continue our slide projection. Okay, so to do a surface extrusion or use other surface creation tools, you need to leave the solid tab and use the surface tab. In this place, you will be expected to supply closed paths for surface creation. You'll also be able to use directly these surface creation tools to create surfaces. There is an error there with the grammar. There are cases where either method will work. In other cases, one way can be vastly superior to another. Experience is the key in selecting what to do. Solid bodies or surfaces are all bodies. So you can also create and edit forms or T-splines from either solid making tools or surface tools. The form icon is present in both cases. Obviously, the form in solids allow you to make solid form objects, while the one form from the surface do the obvious thing, allowing for the creation of surface form objects. There are also meshes, like I said. Meshes deal primarily with geometrical objects imported from other sources. Now, we have talked about bodies. What about components? Whether you call them bodies or components, a 3D body is what you are referring to. When you call it body, it means something. When you call it component, it means something else. The difference rests primarily on how they are stored and what you can do with them. A component is essentially a container of bodies. A component can contain bodies, can contain construction planes, can contain joints, can contain coordinate system, and can contain other components. So a component is a far more a complicated system. But when you have an actual part, it is best you will see to make it a component, because a component gives you much more versatility into what you can do with it. You need to add joints to your container in order to assemble them into a whole. Once you add a joint, what you are dealing with now is no longer just a body, but it is a component. And you'll see that we have been creating components from bodies all along. But sometimes you don't really see any difference apart from the colorings that come in. But you will see now that there are other things that you can now do with a component that you could not do with bodies. That's why you need to convert some things to bodies, from bodies to components, or add the bodies to a component before you can use them in an assembly. You can combine them, but you will not be able to specify geometrical relationships or motions if they remain as bodies. But if you want to be able to specify geometrical relationships like kinematic constraints or motions or relative motions, then you want to make them into components. To do this, you must make bodies into components, or add bodies to components, or make bodies, combine bodies and make components out of the combination. Assemblies. An assembly is a grouping of components, specifying the kinematic relationships among them. In Fusion, sometimes I talk of Fusion 360. The old name of this software is Fusion 360, but it appears that the manufacturers are beginning to use just Fusion rather than Fusion, and then dispensing with the 360 out of it. Sometimes, because those of us who have been using it for quite a while will be calling it Fusion 360 sometimes. Sometimes we remember and call it just Fusion. In Fusion, you can have a top-down assembly or arrange them bottom-up. In fact, the way Fusion 360 presents itself to you, it presents itself as a component creating system, whereby you are just already in a component and you are bringing in the bodies, so it's a top-down. But you can also do it bottom-up. In this example that we're going to do, my own way of working, I prefer the bottom-up. So in the bottom-up, what we do is that we create the components in different files, and then we bring them together. As for somebody who is creating an assembly that has 100 parts, that may not be very advantageous. But if you are creating an assembly that doesn't have more than 10 parts, that has its own advantages. Just know how to use both, and then you will now decide which one you will do eventually. Each method has its advantages and disadvantages. We shall use the parts we have been creating to illustrate an assembly in a bottom-up referential assembly strategy. This is just one way of doing things. After mastering different ways, you'll be in a position to know what is best for a particular design situation. Again, experience counts. You already have a feeling for solid bodies and have made some into components. Let us now do a simple assembly. So since you already know how bodies work and how to make a body into a component, you've already done that. So there's nothing new to you there. So what we are going to do today is that we're going to do a simple assembly. An assembly is the closest abstraction of reality you can achieve. In an assembly, you create the constraining relationships that occur in actuality. Solids not crossing each other, or not crossing one another, depending on how many they are. Restraints by other components are enforced. Rigidity is enforced. Placing bounds on relative motion can be enforced. An assembly is therefore a group of components with their relationships and limits as occur in real life, as close as possible to what actually happens in real life. So that when somebody is saying your drawing is not just a drawing any longer. It's actually a model of real life. And in fact, one of the things we try to use Fusion 360 to do is to obviate for the fact that our laboratories are not good enough. Sometimes some things that I should take you to the lab and show may not exist. But I have seen that we can use Fusion 360, if we use it very well, to create almost lifelike objects. And sometimes it can even be better than real life objects. For instance, I don't know whether we will get to the point of designing a turbine. When we design a turbine, you will see later on that we can actually allow water to flow through the turbine and check the pressure and velocity of the water through each component, something you will not be able to see in real life. We can enter inside the turbine and see the blades and see how they move and see what stresses are generated in them. All those things you can do with the component design of Vision 360 using simulation software, which might actually make the simulated environment even more powerful than a real environment. So these are things we can take advantage of. So I challenge you as undergraduates now, you might be able to do simple laboratory objects for your secondary school using your ability to do design. So those are things, those are challenges you might want to take up, because these are challenges that occur in our own situation that may not occur in the developed world where they already have everything they need. But because we lack some of these basic things here, so the challenge for us to create them here occurs and it's more pressing. And that is a challenge that I think some of you might want to take. Okay, let us take a look at the single engine. This is a single engine, and I showed three configurations of the engine. Here, where you have a clockwise motion of that is displacement of the crank clockwise through an angle. And then here, you can see this as a displacement through like 270 degrees clockwise or 90 degrees counterclockwise. And then you can see the location of the piston inside the cylinder. Here, we deliberately allow the cylinder to be transparent. Here, it is like an angle 200 or 220 degrees. So these are three situations. But for us in Vision 360, this is a single drawing. In a single drawing, you can have all these configurations. And because these three drawings are kinematically equivalent, all the kinematical constraints are the same. The kinematic constraint says that this connecting rod must be rotating in a circle in the big end, must be oscillating in a reciprocating manner up and down inside the cylinder on the small end. That's all. That once you have that, you can have millions or infinite number of configurations that can now take place. That is the power of being able to constrain your work by adding the joints. Okay, so this is an example of what you will get. We are actually going to get this in this class, how we get it to this point. And I'm expecting you to be able to do this. And I will give you the challenges that you come up from your knowledge at the end of the class. Okay. So there are in preparing this class, I looked at some YouTube videos. Well, they are not that fantastic, but there are people who do not like, who may be able to benefit from them. So I've given you here two examples. You can look for more yourself, but I warned you, don't be going for videos that are written for the general public, because you are being trained to be engineers. So there are things that people will tell you that are not applicable to engineers, and there are things that people will say don't matter that are very important for the engineers. So that's the thing. But these are two things that may be useful for some. It is possible some may find it useful. Let me know your opinion in chats or comments on our website. Okay, so we will now go into our single cylinder assembly. This picture here shows the salient parts of a single cylinder engine. We shall demonstrate a simple way to get the parts we already created assembled with the stationary parts we shall create in this class. The block and the cylinder will be created. Those are stationary parts. The former allows the crank to rotate while the cylinder compels the piston to reciprocate, as we shall show. On the top, at the small end of the connecting rod, you'll see what is happening into the connecting rod entering the pin of the piston. And the piston itself is contained inside the engine cylinder, as you can remember. I hope you can see the cylinder, a representative of the cylinder there. It may look like that, it may not look like that, but at least what is important is that the internal surface will just fit the piston so that the piston can move up and down there. On top picture, on top of the picture, as we show here, you can see the piston holding the connecting rod at its small end. In this way, the reciprocatory motion inside the cylinder is transmitted to the rotation of the big end of the connecting rod to the crankshaft. The two stationary parts hold this in place for the engine to work properly. So we will begin with the first slide. And what I will do, I will turn off my loudspeaker here so that there will be no sound coming from there'll be no sound coming from this. Let me see whether I can also turn off my speaker here. I put everything at 0 so that there's no sound. So I will try my best to explain what's going on, but the voice is already there in the recorded video that is clipped into your slides. So let us begin and see how we do this assembly. Okay, so let me go on here. So here you see the connecting rod. We start with the connecting rod. You see that the big end is moving in a circle. It's moving in a circle, and the small end is moving up and down. It's reciprocating. It's in a line up and down. The circle is constrained here by the crank. So we will bring in the crank now, and we'll show you how the crank is agreeing and forcing this motion to be the way it is. So when we go and we go there and bring in the crank, once we bring in the crank, you will see what is happening at the big end. So we are going now to get the crank. So you see the crank. You see, after getting the crank, you can see now how that crank is constraining that rotatory motion at the big end. So that is a kinematical constraint. So the crank is constraining and forcing that motion there. The next thing you want to do after that is to bring in you may want to bring in the piston, the piston's pin and the piston itself. And you will see that when you bring that one in, it's going to constrain the top part of the crank, of the connecting rod, and it will make it to move up and down. Okay, you can see now that is moving up and down, while the bottom part is moving in a circular way. So moving up, down, and that is circular. Okay, so that one is constrained by the cylinder. So we put this representation of the cylinder. You can see the cylinder should be longer than that, but if it's longer, unless we toy with the opacity control, you won't see what's going on in the cylinder. That's why we made it short. But just imagine that the cylinder is long enough that it's keeping the piston in its hole inside it. So the next thing we need to do is to put a block. The engine block is on which the rotatory, it has this, it's a stator, and then the rotor is rotating on it, as you can see. And that is how that engine is able to move. So let's see. I think that is basically the way. So we are going to create this assembly in this class. This is a very simple assembly, a single engine. Later on, we will do something more complicated than this. But you see, we start with this. This thing can be, well, you can remember when we are creating these individual components, they look very simple. But by the time we are now bringing it together into a complete assembly, you can see how these things now become quite complicated. So, but whether it's complicated or not, what is important is that you do it step by step. So, to insert a component in your design is so you can begin a design on a blank note. That is a new page, a new design. Start a new design on a blank note, and then we shall import or insert components that we have previously created. Note that the method is robust and can be used to insert components created by other people. That's the important thing. The important thing here is that even though in this lecture, everything we are inserting were made by us, the beauty of Fusion 360 is that you can also buy, borrow, or steal designs from other people to put in your drawing. So it will work almost the same way. So in real life, your design is not just somebody's work. A design is a collaborative effort. And I will encourage you to work together. Somebody designs one thing, and then you come together and you put a complete assembly. In fact, I believe that we can do a project like that, whereby we go and get a design in such a way that maybe there are 5 people and each person is responsible for 1 or 2 components. And then by the time everybody has finished their own, we come together and bring all the components together into a full design. So that is something that we might imagine that we can do later on. So important to note that a useful design is usually a multitasking effort involving several sources. There is an easier way to assemble using an as-built joint, in which you endeavor to make your components so that they reside in their final destination. We find that too restrictive and we consider general joints. That is what I believe, but having prepared this lecture, I've seen that there are certain situations where the as-built joint will be the most reasonable thing to do. So because of that, before this lecture is ended, I have brought in an example of as-built joint so that you can see how it is used. And you can now decide. There are certain situations where the general joints were very difficult to do. And if in your own drawing you are having difficulty and you see that the 2 things you are trying to assemble are already in their final locations relative to each other, instead of going through the pain of the general joint, you might use the as-built joint. So that's why I gave you, there's an example in front that we'll see before the end of today's class. So that means that you can use as-built joint or general joints as you choose. Joint, an abstraction of kinematics and constraints. The word joint, as we said earlier, as used in our context, is an abstraction of kinematics and constraints. Usually, we express the relative motion or lack of it, which we call rigidity, between 2 components as a joint. Our business is to specify the surfaces or points on which these components where the relative motion will take place. For instance, if there are 2 cylindrical surfaces and they are going to rotate with each other, then there must be a center of that rotation. If you are using general joints, it is your duty to specify and make sure that the center of the rotation you want coincide with what from one to the other, because if not, the general joint will force that to happen, and in doing so, it may move one of your components. When you try to do this, many times when you are having difficulty, that's what is happening. You probably have specified the surface, but you have not specified the center of motion correctly, and the Fusion 360 is not understanding you, and it thinks it needs to move one body to get to the other so that the centers are located in the same place. You don't have such problems with as-built joints. So one way to avoid that is to design in such a way that the 2 objects are already in their correct locations with each other. In that case, you specify as-built joint and you will not have the problem of anything moving to join anything. So we shall therefore indicate if joints allow only rigid connection, sliding motion, rotatory motion, and so on, or what we call cylindrical motion. There are many other motions that you will see. I've not used all of them. I've used several of them. I would explain to you the ones I've used. So if you need to use any one that I've never used, if you are in trouble, I may be able to help you if you are lucky. And if I cannot help you, I will say, sorry, so you go and help yourself. But there is enough latitude in the ones I have used to do most of your work. If it's really important, I can read it up and show you how to do it. Apart from these constraints, we can also set limits to the permitted motion in each object. Once this is done, the design software will enforce the rules that we have specified. So we can have a situation where we are not just having constraints, we are having limits. So the fact that 2 things can oscillate, we can say, okay, let them not oscillate beyond 30 degrees of each other. So that way, once it gets to 30 degrees, it will stop there. It won't go beyond it. The only way it can do is to come back. So those are the things. Even if the sliding motion, we can say let them not slide more than 2 inches from their rest position. So once it gets there, it will stop. So those are the things that can be enforced by Fusion. So the crank on engine block. We begin by inserting a crank that we have already created. We then create the stationary block on which crank rotation will take place. Once we set the allowed motion and limits, we shall test the relationship. We select revolute joint that allows relative rotation between the stationary block and the crank. So this will allow this rotor to rotate over this body. So the relative motion is absolute when this one is stationary. So what was a relative motion becomes absolute motion when one of the two parts are stationary. That is engineering. So that is something that the people teaching online cannot tell you, because they are addressing themselves to general public. So that is different. Okay, let us just take a look at this. Let's take a look at this slide here. In this slide, we are going to demonstrate the first joint. So we demonstrate the first joint. So look at it here. So in the first joint, what we are going to do, we are starting with a blank page. On our blank page, the first thing we want to do is to go to the data panel and bring in the component that we want to start with. This component is the crank. When we right click on it, it's not showing here. I didn't give enough space on my Fusion 360, but in later pictures you will see the data where I'm getting it from. So once you choose that, you are going to bring that into the drawing. Okay, so you bring that into the drawing. So you say insert the drawing. This is the crank. In this case, we use the crank. You can move it up, move it down, rotate it. You can rotate it and you can do whatever you like with it. But in this particular case, we can also move it left or right, or rotate it through a horizontal axis, vertical axis, and oblique axis. All those things you can do. And then you can also specify X direction, Y direction, angle direction, all the differences, all the displacements you want. If you are happy, you agree. If you want it to be in the original way, you just remove all those motions and you have it the way it came in at first, which is like this. So that is your crank. And the next thing we are going to put now is the connecting rod. So we are going to look for the connecting rod in our data panel, and we are going to tell the connecting rod to be inserted into, we're going to use the connecting rod that as it is inserted into the design. So that is the next thing to do. We ask the connecting rod to be inserted, and oh, is that not? No, that's not actually what I did. What I did first is to create the block, to create the engine block. Okay, to create the engine block, we let me backtrack a little bit and see how the engine block is created. Okay, to create the engine block, you have to create sketch, and I want to stop it there. I want to stop it here. Now, you remember that when you create a sketch, you must specify, to create a sketch, you must specify a plane of creation. You must specify the plane on which you want the sketch to come. Now, the plane we are choosing here is this edge of the rim. That's a plane surface. And we are taking a plane surface that passes through that rim edge. And that is where we are going to create the block. So when we create the block there, we are going to extrude it to join from that point to the other groove. That way, we are sure that our block is fully in its final position. So we didn't choose this lightly. We chose this advisedly by choosing the rim of the block as a plane of creation. So because once you start looking at it, you will not know. So that's why it is better to really see it now. That is the plane at which we are creating our sketch. So let us move on. We're creating our sketch on that plane. And once we create our sketch on that plane, the plane will face us. And then we can now, well, any sketch we create now is on that plane. So we start by taking a line element, a line creation element, and we start from the center there, and we move back. And then after that, we move down. And then after we move down, we move right, and then we close. As soon as we close, you can see we have a close profile and it has painted it blue. And then we can make sure that that line is horizontal, it's already horizontal. There's a sign there showing, and then there's a right angle there showing that is vertical. And then we can force that other line to be horizontal by going to take our horizontal vertical constraining tool. So once we choose that, that is horizontal. And then if we try to put it there again, it tells us it's over constrained because that's already vertical. There's nothing to do. So we don't care really about what happens here. So that is it. So you can see if we finish sketch, you will look, if you look again after finishing the sketch, you will see that that thing is in the correct place. So you can go and click finish sketch. Okay, sorry. The next thing is that we create a circle radius 80 also at that same place. A circle radius 80. And once we've done that, we finish sketch. So I want us to pause here a little bit. When you pause here a little bit, what I'm saying is that all this drawing, the circle, the lines are on the surface that passes through this rim here. It is a surface that passes through this rim. So if we now, that is our profile plane. So if we now try to extrude, we are extruding from this surface forward. We are extruding from this surface forward, and just know that this drawing is taking place not on this surface, not on the original surface, not on the coordinate surfaces, but on this surface here. Okay, so let us continue now. We continue. We now want to extrude, and then we click that. Then we say we choose that as the extrusion profile, and then we choose the distance to be 35 millimeters. You can see it just simply fills the groove that is there. It just fills the a place provided between those two grooves. Okay, so when we are happy with that, we can decide to make, what do we do with that? That is the body. We decide to create a mirror of that body. Create a mirror. Create a mirror of that body. And then the mirror plane, we need to do some orbiting to get the mirror plane. Okay, to orbit it so as to get the mirror plane. Okay, so we can see the mirror plane now. So we choose the mirror plane. That is the mirror plane. So we're happy with that. We join it. So that now is our one leg of our engine block. So we can go back home there. So what we can do after that now, we can decide to make a component there or mirror it. So make a component, we made a component from there, and then we can decide to we can either name it or mirror it. We can do either of them or both of them at this point. But I think what we are going to do is that we're going to create a mirror again. Create a mirror. Create a mirror. And then the mirror is going to use a coordinate YZ plane. It's going to turn on the origin. That's the coordinate YZ plane. And then if you choose that and select that as a mirror plane, it just puts it in the right place on the other edge. So you can see the two components that make up the block. So 1 and 2. So those are the things. And then what we need to now create is the kinematic constraint that the rotor on the crank can rotate on the block. So that rotor can rotate on the block. And then, in order for that to happen, we have to use a joint. We want that to rotate on the block there. So there's something I did there which I didn't talk about. So let me move back. Let me move back. Let me move back. After we have gotten, watch this. Well, the first thing we do is that we make this. We do what we call grounding. We ground this block. We ground the block. In order to ground the block, we choose the block by right click and we choose ground to parent. So if you look at the icon for it, you will see like an anchor on it. So it is grounded. It will never move by itself with respect to any part of the body. So that is it. It is after that you now make sure that this rotor can rotate on it. So in order to do that, you say assemble, a joint, and then you are now going to choose the parts of the rotation. Okay, so if you choose that groove there on the rotor, you must choose what is corresponding to that groove on the stator. Okay. So because if you don't do that, then the center of the motion will be different. And because fusion, we want to put the two centers of motions together. So you turn off the crank now. Once you turn it off, go and turn it off. Okay. So you now go to the part of the stator that also has that same center of rotation, which is that edge there. If you choose it, and there's a complaint here that is ignorable. So if you choose it, you'll see that the two of them are choosing the same place, so there will be no motion, and the motion here is not rigid; it's revolute. Okay. So if you are happy with that, you say okay, and you go and test it. You say okay, you've turned this thing on again, and then you can now go and test the joint. Right click on the joint. You right click on the joint, and revolute, right click on it, and go and animate the joint. So you see, that's an animation of the joint now. It's showing the two of them, and it's showing that the rotor will move on the stator there. As I said before, you could have achieved this with an as-built joint. As-built joint will be easier to implement than what we have just done. So one thing you can try, after I have taught you about, with an example, how as-built joint works, you probably can test that. So what we have achieved here is that we have created the non-moving part of the block, and then where the rotor of the crank will rotate on. And then we have created that kinematic relationship. And so I think we have spent, I will give us 3 minutes. I'll go to the chat room now, and I'll wait for you in the chat room so that if there are questions that you have not been able to ask me, I hope you've been hearing me because I've turned off my volume. So let me see where the chat room is and see whether there are questions waiting for me there. Chat. There's zero chat. Is there any question? If there are questions so that I can answer them or work on them in the second part of this lecture. Is there any question? Is there anything that you want me to clarify? Let's say any questions? Did you hear me? I wasn't hearing myself, so I'm not sure whether you people were hearing me. Okay, you can hear me, good. Do you have any questions? Okay, you heard me. So if there are no questions, we are going to go on a 15 minutes break. No questions? Okay, we are going to go on a 15 minutes break. and that 15 minutes break will end at 9:10. We are resuming back at 9:10, 10 minutes past 9. Thank you. Okay, I hope you are back from your break now. So we are now going to bring in the connecting rod assembly. We've been able to connect the crank to the block. Before we connected to the block, we grounded the block to show that it will not move. Our next task is to bring in the connecting rod. Recall that the connecting rod is in two components, the con rod body and the con rod head. We therefore have two pairs of objects to join. The con rod head to the con rod body, which will be a reedy joint, and then the con rod assembly to the crank, which will be a revolute joint. The first is a rigid joint, and the second is a revolute joint that allows for rotational motion. We insert these components, the con rod body and the con rod head, into the present design. We do this by finding the drawing in the data panel and right-clicking on it. In the drop-down, we select Insert into Current Design. In this case, the connecting rod is inserted correctly and placed into the design. Note that if this were not so, we could use the motion handles, linear and rotational, to guide it into the right place. But this is not needed here. Furthermore, because of the location of the connecting rod, it is possible to use as built joint in this case. We will not do it here. We will do it at a later stage. We will use the more complicated general joint here. But later on, we'll use the as-built joint. You can use either of them, and it is good for you to be able to use both so that you will know, so that you'll be able to use whichever one is more convenient for you at any particular time. Here, both can be used, but we are going to use the ordinary general joint, which is harder to do. So what we are trying to do is to place the connecting rod inside the crank and implement and enforce the kinematical relationships that this thing must stay inside the big end, must stay inside the pin there, the big pin, and it must not get off it, but it can rotate in it. And then that this con rod head and the con rod body must be rigidly joined with each other. Those are the two things. We select the meshing positions for the connecting rod and the crank. The former arrives in the connect position. The railroad joint is selected for this. So between the con rod and the con rod body, this joint is rigid. And then we can also insert the piston. The problem with the piston is the very, very, very difficult one. First of all, the piston is not even going to be, when you insert it, it's going to be at a much lower point. It is by pushing it up that we get it to this point. And when we push it up, what do we see? We see that the pin is not in the correct orientation and not the correct place as where it's supposed to enter. And you will see this is where the power of Fusion 360 really shows. By the time you choose the correct position to join these two, it will be Fusion 360's duty to put them correctly. For the piston, we also have two subcomponents, the piston body and the piston pin. These two must first be connected rigidly using joints. This is shown in the picture here. Note that the pin is not properly oriented towards the small end of the connecting rod. It does not matter. Joint process will correct that automatically. But in order for that to happen, we must not only just say we want to join this pin into this hole here. We must be sure that the rotational point, which is at the center here, must also correspond to the rotational point, which must be chosen at the center here. Once those two are correct, it will rotate them and put them together correctly. But if they are not, and you will see, this is the example of a joint that can test your patience and can test you a lot. So for you, by the time you are able to, even though in class, in the video I'm going to give you, this looks so easy. It is not as easy as it looks. Do it yourself and you see what I'm talking about. Later on, you can use as built joint to do it. But to do as built joint, you have to make sure that your design is such a way that the orientations are equal. Okay, so let us go back to the video now, the video, and see how it works. Okay, so in this case, we've already done these two components there, the block and the rotor have already been done. So what we're going to do now is that we're going to look for the connecting rod. This is the connecting rod here. Right click on it. If you right click on it, you will see the second, just insert into the current drawing. Click on that. If you click on that, it's going to bring it. You can see it has brought it in. And in this particular case, it placed it at the exact point of his final destination. So because it is like that, as built joint can be used. But if it wasn't, you could use the handles to move it, to rotate it, and to move it up and down, left and right in oblique locations. And all those things are possible before you bring it to the final position. And if you're happy, you say, okay. If you're not happy, you just remove all the motions and you let it go back to the way it was brought in. So that is it. So the next thing for you to do is to now create a revolute joint on the crank and on the connecting rod. So which one are you going to do first? So we are going to choose that part of the groove as a place to put so that part of the groove we choose. So if we choose that part of the groove, okay, so if we choose that, let's see, which one are we choosing? So we assemble, we choose joint, and we choose that circle there. So if you look carefully, you'll see that there's a center. It has located the center there. That center you can see here, that center. Okay, so you are now going to turn that off and turn on the crank. So you are going to choose the part of it that also coincides with the same center as you have just chosen. So if you choose that, and then you bring it on again, and you are going to select the motion. It's not rigid, but revolute. So it's a revolute motion. So you can see as it is testing it, it left the connecting rod head alone, which means that we have to come and do another joint between the connecting rod head and the connecting rod body. So we're going to choose something between the two of them. So we're going to create another joint, assemble joint. Again, an in place would have done it, but so let us choose the pin hole between the two of them as the point of joining. So we choose the pin hole after turning one off. Choose that pin hole there. Okay. Okay. So we turn the body on, and then we use orbit. We use orbit to bring it. Okay. So we're going to turn off the orbit and then choose that same place. Okay. Okay. So we should choose okay. And then we're going to turn it back on and then say okay. So we can now test, we can test the revolute motion again. We will now test the revolute motion. Okay, so that shows the head at the bottom of the head and body of the connecting rod joint. So it's now rigid motion, not revolute. So we can now test the revolute 3. That's revolute motion again. So we can go and click it and test it. If we test it, we'll see that it carries the whole thing with itself. The next thing we're going to do is to bring in the piston. Bring in the piston. So we have to look for the piston in the system. So there are many pistons I have here, but there's a particular one that I'm using for this purpose. So go down a little bit more. Okay, yes, this is the piston that I want us to use. So you right click on it and then insert to the current design. If you click that, you can see where it has come. It is in a very, very, very wrong place and very wrong orientation. We could do it and orient it correctly. And click OK. Okay, so we have to join. We have to join the piston and the pistons. We have to join the piston and the piston pin together. So if we join the piston and the piston pin together, it has to be a rigid joint. So we can go again and switch one off. We should switch the piston off and then say assemble, join, and then we choose the piston pin. You can see that the center of rotation is at the middle there. So we must work in such a way that we can also select the piston in such a way that the center of rotation is at the middle too. So let us, and this can be difficult. Because this is difficult, I'm going to eventually show you another way to do it. So one thing we might do is to go and bring in the sketch. We might need to turn on the sketch that made that hole to start with. So if we turn on the sketch and we choose the center of the sketch, because none of these things seem to be working, I decided to make it bigger so that you can see it. So here, nothing worked for me when I did this until I turned on the sketch. I'll go to the piston internals and go and turn on the sketch that created the piston pin from the piston itself. So turn on the sketches. Okay, sketch 2. We turn that one on. Aha. So we can now go and select that center. Okay. So that's what we want. That's why we want that rotation to take place. Okay. So if we're happy with that, we can now turn this thing on and say, okay, the motion is revolute, is correct. And then we can now go and click OK. Oh, sorry, the motion here is rigid, not revolute. So there is no motion between the piston's pin and the piston body. So I think that is it for that. So we have been able to make the piston pin and the piston body to be the same thing. So we have assembled the piston component and the piston component and its component pin. We now need to assemble both into the small end of the connecting rod and impose the kinematical constraints of rotation at this point using the revolute joint. And to do that, I decided to use Orbit to make sure we can see both of them at the same time. So in order to do that, we are looking at both of them now. And let us now play this video. So we are going to take the piston pin and or the piston itself and join it at the pin to the small end of that connecting rod. Okay, so we're going to choose joint again. So assemble a big joint. We take that one and it has to happen in the middle of it. Yes, there. You can see the revolving point there. It's in the center of that drawing. So when we're happy with that, we say okay. And then we now go to select the second component. You can see it is at the outside now. Yes, it's at the, so you can now be very careful. It's at the middle now. So you select it and be okay. Aha. So when you are happy with that, you say the motion is revolute, not rigid. So it has given you an idea of how to move. You say okay. When you say okay, all the rotation, the motion, the translation that are needed to put it inside that place will be taken care of by the. So we can now animate the relationship. So this is the relationship between that. You can see that meta is passing through meta. So that means that just the relationship is not good enough. We have to set limits to the rotation. The rotation cannot just be 360 degrees. We have to set the limits to the rotation. We'll do that at another time, but that shows you that there is still our work is not completed. We have to add some further constraints of limits to it. So that is done. So what next? So we have let us see what we have done pairwise. We have done the relationship between the block and the rotor. We have done the relationship between the crank and the body. We have done a relationship between the body and the head. We have done a relationship between the piston pin and the pin. We have also done a relationship between the piston itself and the small end of the crank. What we have left to do is to now create a sliding motion between the piston and the cylinder. In order to do that, we have to draw the cylinder. So let us we do the cylinder, draw it, and then we make sure that the piston can only move along the axis of the cylinder in a slider motion. So that's what we do here. So in order to do the cylinder, we're going to create a sketch. We're going to create the sketch on this plane here. Okay, we first of all animate, just to remind us what we have done. We want to animate the joint there. We can animate all the joints we have made so far, pairwise. Okay, you can see that in this case now, the both bottom and the body of the connecting rod, they are moving together unlike before. Okay, and then we can now animate the rigid joints. That is between the bottom, the pin head and the connecting rod head and the connecting rod body. And then the next rigid is between the piston and its pin. So we want to animate that joint. Okay, so you can see the joint there is animated. Okay, so we've animated that joint. And then the joint there, which shows us we have to set limits for that. We have not learned how to set limits. We learn how to do that later on. So after that, we now want to do the last joint, which is the cylinder. So we need to do a sketch. We have to create a sketch to get the cylinder done. So create sketch. Create sketch. And then we can choose that as the plane of creation. And then we're going to do a cylinder and offset it. We're going to do a circle from the center on the radius of 90 or 91, just to give some tolerance there. Okay. And then we are now going to take that body and do an offset of, is it 10 millimeters? What did I choose? 10 millimeters, okay. So there's an offset of 10 millimeters there. And when we're happy with that, we say, okay. That gives us our sketch profile. Let us go and turn on that sketch. The sketch is turned off. That's why we can't see it. So we turn it on so you can see the sketch profile now. The sketch profile is there. So we are going to do an extrusion. Create extrude. The extrusion is coming from the profile plane, but it's going on both sides. Two sides. So you can choose the first one and move up. We're moving up to a distance of 30 something, we move down. You know, we can be flexible in what we do here. We just want to create the abstraction of the cylinder to give the, okay. So we made a component out of the cylinder. We make a component out of it. It is a body right now. And we go to choose that body and we turn it to a component. So if we choose that body, make component from body, it changes color, and then we're going to label that cylinder, seal, SYCYL. There are two things we do to the cylinder. One, we are going to make it transparent. Two, we are going to ground it. Opacity control is at 40%, so that we can see what's going on inside it. And then we are going to ground it. We're going to ground it to parent. So when we right click on it, we're going to ground it. Okay, let me see. Have we done the grounding? The grounding is not yet done. The grounding will still have to be done before anything we are doing will work. So okay, so we choose the internal surface of the cylinder, and then we choose the sliding point to be the middle there. So the motion is not revolute now, but sliding. So it just shows that it's a relative motion. So it's either that we still need to ground it. So say choose ground to parent, and you will see an anchor. You will see an anchor in the browser. You see an anchor on the icon of the cylinder that shows it's grounded. So everything that you see anchor on it, they are grounded. There is a grinding of the con rod body here, which is wrong. So we have to remove that. Otherwise, there will be a problem. So the animation will happen there. But we still have to find a way to remove this. The grinding of the con rod body is wrong. So the con rod body cannot be grinded. So I don't know when that grounding was mistakenly done. So we have to remove that. So the only two things that have to have the anchor on them are the cylinder. The cylinder must have an anchor on it, and the engine block must also have an anchor on it. Okay, so let us move on now. So we are now in a position to animate the single cylinder engine. We are now in a position to animate the joints and relationships of the single cylinder engine. We can do this by selecting any joint that compares the motion in other joints. Note that it is not all joints that can get this done. Sometimes a trial of several joints by animating their relationships will give you the options you need. In the next slide, we will do this using the crank connecting rod, the crank to connecting rod big end, as well as the crank engine block revolute joints. In each case, we select animate joint relationships option in the drop down for the specific joint. So let us do that now. And that's what we are doing here. And when we do it here, we can now come and test the joint and tell it to animate. So we're going to right click on the joint. Okay, we're turning off the joint so that the joint icons will not be showing. The joints are still active, even though we have turned off the visual representation of them. So animate joint relationship. Okay. Okay, so you can now see how all the pairwise relationships come together now to give us the complete animation of everything. We can also do that with the second one, animate joint relationship with the other revolute joint. We also do the same thing. Okay, animate joint relationship. Okay, so with that, we've been able to do the full animation. So now, like I said, as we have done like 6 or 7 joints. In those, most of the joints could have been achieved with as-built joint. And in order to show that, I just decided to use an as-built joint example. We have used the more powerful simple joint so far in the design. There are other kinds of joint. As-built joints is useful when the components involved are already positioned relative to each other. A simple example we can show, as a simple example can show how this is done. On a fresh design page, bring in the same crank we previously used and also the same connecting rod. See the three components in the picture here. So you can see the three components. This is the connecting rod head, the connecting rod body, and the crank. Those are the three components. So also, if we do that, let us see how this joint can be done. Like I said, I will start on the fresh page. So if you start on the fresh drawing page and you come, first of all, you bring in the crank. You look for the crank and you bring it in. So you go to the data panel and you look for the crank. Go to the data panel and you look for the crank. So you have to search for it on your data panel. Okay, so you right click on it, insert it to the current drawing. Once you click on that, it's inserted into the current drawing. So you are happy with that, you click OK. And then you go back again and you look for the crank, and for the connecting rod. You have brought in the crank, you now go to the connecting rod. Okay, that's the connecting rod. Right click again and insert it to the design. That's brought it into design. You can use the coloring. If you're happy with that, you can, what do you do next? You can decide to do the assembly, and then this time you are going to do the as-built joint. As-built joint, yes, you are now to select the objects for the as-built joint. The motion is revolute, and the objects, select the objects now. To select the objects, the first object is the new crank. The second object is the con rod. And then you are now going to look at the snap point. So you really choose the snap point. The good thing about this, you just choose one snap point, it will zoom it for the other one. That is the beauty of the input. So just choose a snap point, and then that is all you need to do. You don't need to choose snap point for both of them. And then just do an inspect. Okay, what to test the joint? Let's test the joint with okay, so let us use the coloring of the inspection now. Go to inspect and choose the coloring. You can see that the crank and the connecting rod head is not moving. It is just the connecting rod body that is moving. So that shows there is another joint that you should do, and that joint is between the crank and the connecting rod body and the connecting rod head. So assemble again, you will use as-built joint because they are in the correct relationship with each other, and it is now a rigid joint. Rigid. And then the first object is the connecting rod body. So you can see both of them, the connecting rod body and the connecting rod head. And then you are going to choose the two of them. And then if you now go to do the test the revolve again, you can see now that it is taking both of them with each other. So that is what you can, that's what you can achieve from there. So let me just do something now. Let's go back to the Fusion 360 page. I want to go to the Fusion 360 page and see whether, okay, in my Fusion 360 page, what do I have there? Okay, in my Fusion 360 page, this is directly now on Fusion 360, and we have decided that we can test this rigid joint and animated joint. You can see the rigid joint between those two is showing you that that's how it shows you a rigid joint. It just shows you that they are bonded together. If we animate the revolute joint as we have just done, we can animate the joint relationship. You can see that everything is working fine. Now, I want us to take a look now at let me just go home here. Okay. So if we make this let me bring this one to the vertical here. So or so if we bring in if we decide to bring in the connect the piston, we can bring in the piston again, new piston. Where is the piston? Okay, so we bring in this piston, we can start it to the current drawing. Okay, so it is, see where it is. And if, let's say, I want to make this one, I can move this thing up 180. If I move it up 180 millimeters, 180 millimeters, and I can, what I need to do is to straighten this one up. And so if I move it 180, I can do an orbit of it. And I can actually also rotate it. Let me redo that. Let me just get that one removed. Delete. Okay. Let's go back. Okay. Let's see whether we can move this hole. Okay. So this is how this thing was originally. So I want to show you how we might be able to use as built joint here, and that it will make things much easier than what we did. To do that, we can bring in this piston, the new piston, in the data panel. And bring the piston in. Oh no, new piston, ST, and SSG. I have so many of these pistons, many of these things now. So this is the one I'm looking for. So bring it into the current drawing. Now, because of what I know about this thing, I know that if I move this thing up Z distance of 180, and then if I rotate both of them, maybe the first thing I do is that I join this thing to this rigidly. So I can do an assemble and as built joint, and I'm going to choose this and this. So, and I will say, okay, so let us test that joint. Okay, so those two are joined rigidly. So what I want to do now, I want to rotate this through angle 90. So I want to move. I want to move it. I want to have a rotation move. The body, select, axis. The axis I want to rotate through, let us see the origin. I want to rotate it through Z axis. So, and I want it to go through 90 degrees. Body. The body selection is piston. Okay, through 90. It's not giving me selection. Axis. An angle. Okay, okay, it's not saying bodies. Let us see component. And then the component is piston. And the angle is 90. degrees. And then, okay. Okay, so let us see now. I want to do an orbit and see what's happening. It's still not correct. So I want to move it down again. So let us say, I want to do move. I want to move it. It is a component. I want to move it linearly. I want to translate it. Big direction. Big direction. Let's say I want to move it down. Let's say I want to move it down. Okay, so if I'm able to force this thing into the final position, then I can now use as built joint here. You can see it's a little bit tedious to do that. Whereas if you use the direct joint, all you need to do is to select. Let me just try and use the as built joint here. It's not going to be perfect, but I can try. So let us say now assemble joint, no, not joint, assemble as built joint. And then I can now select this component and this component. And then the joints I want is revolute. If I select the snapping to be like this, so it is not accurate. So it's not accurate. So it's not as good. It's not as easy. It might look easier, but it is easy only when the bodies are already at their final positions. If you try to manually put it at the final position, you can get it right, and you may not be successful in getting it right. That is what I want to just show you. So that's okay. But we were able to do that by the general joint in the other picture. So let us just leave this one now and then conclude this lecture, and then I can give you an opportunity to ask me further questions. How many minutes do we have? We still have a few more minutes. So let's see what happens here. We can, next lecture, we're going to consider linking the components to the original design. And I think until we get to that next lecture, we'll leave this, because I think you have had enough to chew today. I will create the links to the original design, whereby you are going to make changes on the original drawing. And let me just give you an example of the changes we may want to make. Let's go back to the Fusion 360 page. Let me see. Do I still have it on? Yes, it's still on. Now let us pan this thing down and make it a little bit bigger. Now, suppose in this diagram, here we have only two grooves for our piston rings. Suppose I want to make a third groove. I can go to the original drawing and make a third groove and force it to show up in this assembly. And I will not need to do anything, and it will show up in the assembly. There are several other things I may want to do in the original drawing, and I want it to show up in the other assembly. So that linking to the old drawing can actually be a very powerful tool. We'll do that from next lecture. Thank you. So what I'm going to do, I'll give you 5 minutes. So if there are questions, you can ask me those questions now. And if you have questions, please go to the chat room and let me see your questions. If I cannot answer the questions in this lecture, then I will try to answer them in the next lecture. Chat. Apart from when moving the components into place is tedious, is there any other case when using normal joints that when using normal joints is better? Well, I can't answer that question for you. You go practice both of them. You will be able to answer that question yourself. Sometimes after dimensioning, my lines are still blue and not black. How do we do reinforcement? That's a question that was asked earlier. That question was asked earlier today by someone, that is by Prosper Olufemi Shobayo. You probably came late. So please go and look at the answer I gave. Can the speed of the piston be changed? Well, we are not, we can do proper animation whereby we select speed and all those things. But that's not what we are doing. We are just trying to see what kinematics are going on. We are not even carrying the direction right now. We will be able to do many of those things later. But right now, we're just checking how to use the joints and how to be sure the joints are given the kinematic relationships. That's all we are doing right now. Okay. Yes, it is possible to change the speed. It's possible to do proper animation. I was kicked out by a network when I asked. Oh, you were kicked out by the network when you asked earlier. Okay. Yes, the thing is this. It is a good practice for you to make sure that your drawings are black. And usually when you are still getting them blue, it is because your drawings are still not completely constrained. And even though you have finished your dimensioning to your own, but the origin of some of the dimensions may not be anchored at the correct place. So you have to check. So there must be something you have not done right. That is as long as it remains blue, it's telling you that there is still some unconstrained motion that can be, that is a dimension that hasn't been constrained. So you have to check. What I advise you to check your dimensions and check where the dimensions are finally anchored to. For instance, you might say something is a particular arm is 90 millimeters long. Okay, that's the dimension. But is any of the edges, the distance between any of the two edges to the origin, is it known? If it is not known, the dimension can remain 90, but it can be moved away from the origin. So that is still a constraint that is still not showing. So that's the thing. So you have to check that all your dimensions and all your constraints are on. So that's what I can say to that. Any other question? Is there any question on joints? Further questions on joints or on the different kinds, rigidity, revolution, sliding? Those are the ones that I've showed in this class. Well, if there are no questions, please note that the minimum I expect you to do is to at least recreate the drawing that you have been given. That's the minimum. By next week, I'm going to give you a homework. And everything in the homework you have been given should be arranged so that you bring them to your final exam. Because in your exam, you are going to start from what you have done and you will be asked to do specific other things. So if you did not do your work, you won't be able to do those things. So it's better you make sure that you are working by yourself, you are working on your own. And even when you collaborate with other people, you know what you are doing, you can replicate the work on your own. Well, if there are no further questions than the one I have seen, I am tempted to say it is time to say goodbye. See you again next week. But between now and then, I'm hoping you people would have practiced all you have been taught. Goodbye.